Imagine pushing gold, a metal known for its dazzling shine and resistance to corrosion, beyond the limits of what we thought was possible. Scientists have now superheated solid gold to an astonishing temperature of over 33,740 Fahrenheit, 18,726 degrees Celsius, without melting it. Yes, you read that right. They kept it in its solid state while cranking up the heat to levels that would make even the sun jealous. But here's where it gets controversial. Are the rules of physics bending? Or are we just understanding them better? Let's dive into this mind-blowing discovery. An international team of physicists pulled off this feat by rapidly heating a thin sample of gold using ultra-fast laser pulses and then probing it with precise X-ray techniques. The result? A groundbreaking study published in Nature that documents how they achieved this seemingly impossible task. Their work not only shattered long-held assumptions about the maximum heat a solid can endure, but also introduced a new method for measuring the temperature of extremely hot and dense materials, a challenge that has baffled researchers for decades. At the heart of this experiment is a phenomenon called superheating. This occurs when a material is heated far above its usual melting point, yet remains solid because the rapid application of energy doesn't give its atomic structure enough time to rearrange into a liquid state. Led by Thomas G. White from the University of Nevada, Reno, the team collaborated with experts at SLAC National Accelerator Laboratory and other institutions to push gold beyond its typical melting threshold in an instant. For a fleeting moment, the gold retained its crystalline structure, allowing the scientists to measure the speed of its atoms and determine the lattice's temperature. This achievement touches on a broader field of science known as warm dense matter, WDM. WDM exists under conditions of extreme heat and pressure, similar to those found inside planets or within fusion reactors. Accurately gauging temperatures in this regime has been notoriously tricky due to the tiny scales and short lifespans of such states. However, the team's innovative use of inelastic X-ray scattering provided a direct way to track atomic velocities, offering a clearer picture of the material's thermal properties. So why does this matter? Back in 1988, physicists Hans J. Fecht and William L. Johnson proposed something called the Entropy Catastrophe. They argued that once a solid reaches roughly 3 times its melting temperature, its entropy, the measure of disorder, would rise so much that it would inevitably melt. This became the textbook boundary for how hot a solid could get before losing its structure. Yet this latest research shows that ultra-fast heating bypasses that assumption entirely. By outrunning the processes that normally cause a crystal to expand and break down, the team created a hotter solid phase without breaking any fundamental laws of physics. To achieve this, they used an incredibly brief laser pulse lasting just 45 femtoseconds to inject energy into a thin gold foil. Following this, an intense X-ray pulse captured the motion of the atoms through subtle shifts in scattered X-ray frequencies. These shifts revealed the gold's temperature directly without relying on indirect models. Because the heating happened so quickly, the lattice couldn't expand significantly during the measurement window, preserving the crystalline order for a few trillionths of a second. Importantly, this breakthrough doesn't defy the second law of thermodynamics, which governs entropy and the natural tendency toward disorder. Instead, it highlights how speed and timing play crucial roles in maintaining order under extreme conditions. As Thomas G. White explained, we didn't violate thermodynamics. We simply showed that the entropy catastrophe isn't as absolute as once believed. Some skeptics might argue that these ultra-fast, ultra-small-scale experiments don't perfectly mirror real-world scenarios involving solids under normal pressures. Still, This controlled approach allows researchers to test long-standing theories about melting and stability with unprecedented precision. And this is the part most people miss. It's not just about gold. This technique could revolutionize our understanding of other materials too. For instance, better temperature measurements could improve models of planetary interiors, where warm, dense matter dictates how heat flows through cores and mantles. Getting the numbers right helps refine predictions about planetary behavior. Similarly, fusion research stands to benefit as well. In inertial confinement experiments, laser-driven targets transition rapidly from solid to ultra-hot plasma, and knowing exactly when and how these changes occur is critical for optimizing designs. There's also potential for rethinking material performance in extreme environments. If rapid heating can prevent other solids from melting, despite being pushed far beyond their expected limits, it could lead to insights about strength, heat capacity, and failure mechanisms under stress. Could we one day engineer materials capable of enduring unimaginable heat without collapsing? That's a question worth exploring. Looking ahead, future studies will likely explore different elements, thicker samples, and varied time delays to pinpoint exactly when order breaks down. Each variation will test the practical boundaries of superheating and reveal how universal or limited this newfound flexibility might be. In the meantime, this remarkable study invites us all to reconsider what we think we know about the limits of matter. What do you think? Is this the dawn of a new era in material science? Or are there still untapped mysteries waiting to be uncovered? Share your thoughts in the comments below.